So today we're going to finish up lecture material, and if we have time, there was no discussion 9 to be handed in. If we have time, we'll do some exam review. Otherwise, we will just end the lecture today with the material that we cover. Last time we were talking about gravitational potential energy. I think that my audio is working fine. Yeah, it looks like it is. What I showed relatively quickly anyway was that given the formula from Newton's universal law of gravitation for the gravitational force and the fact that the gravitational force is conservative, we can determine the gravitational potential energy explicitly basically just by doing an integral or undoing a derivative, because we know that the force is related to the gradient or the derivatives in the three directions of the potential energy. And so what we found is the gravitational potential energy, let's call it U sub g maybe, is negative g big M times little m divided by the distance between the center of masses of the objects. Or rather the distance between the center of mass of the system to each of the objects. So it's a useful formula, and hopefully you saw that you can solve a lot of problems using that formula on the homework. By the way, a choice that I made implicitly here is that I just chose that U naught is 0. That's akin to choosing that we want the gravitational potential energy to be 0 infinitely far away. We could choose it to be anything else, but it's just a standard convention to make that choice. But again, you don't have to choose that. So we can plot this gravitational potential energy relatively easily, right? It's just it goes as basically 1 over r with a negative sign in front. So this looks something like this. That's a poor graph. Maybe something like that anyway, where this is r and this is U sub gravity. And in fact, we can actually zoom in on a particularly small region. Maybe we zoom in here. And what do we find? Well, we find that the gravitational potential energy function, let's say that this point here, let's call that R naught, and let's call these two bounds R naught minus h and R naught plus h. So we're just looking at a small range around some fixed value. In that small range, what we have is that the gravitational potential energy basically looks like a straight line. I should probably do this better, something like that. As long as h is sufficiently small, you don't really see the curvature. So this notation, h is double less than R naught, that just means h is significantly smaller than R naught. We find that U sub g of R naught is approximately linear. So why might that be? What is the ball in the graph? Oh, that's just me like putting a magnifying glass and then zooming out to here. Sorry. You know, like when you have magnifying. Anyway, so the question is why is it approximately linear? Why isn't it approximately constant or approximately quadratic? Well, you guys have all seen Taylor series in calculus, presumably, and this is just a phenomenon of Taylor series. So if we Taylor series expand about R naught and we let h be the expansion variable, which we can do, right? Then, well, what does our Taylor series actually look like? You guys know how to do this, but U of g, or U sub g of R naught plus h would be equal to, well, it's negative g m over R naught plus h, and so we can Taylor series expand that function. You get negative g m over R naught plus g m over R naught squared times h minus g m over R naught cubed times h squared plus dot dot dot, and it, you know, goes on forever like a Taylor series does. And so we could, oh, 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 come on, stay. We can simplify this, or I suppose factor this, to the following form: negative g capital M little m over r naught times 1 minus h over r naught plus, sorry, plus h over r naught squared minus dot 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 dot, right? And so for sufficiently small values of h, for when h is significantly smaller than r naught, then it's true that h over r naught squared is significantly smaller than h over r naught. So it's also true that h over r naught is significantly smaller than 1, right? That's also true. However, what we're going to do is we're going to drop terms that are not significant, but we don't want to drop this term. We don't want to say, oh, just call that 0. And the reason for that is then your gravitational potential energy, you'd be approximating it just as a constant, and that doesn't help us at all because there is a gravitational force. It's not equal to 0. So what we're going to do is we're going to drop this term and all higher order terms because it's even smaller than the small parameter h over r naught. So what do we get? We get that u sub g of r naught plus h is gmm over r naught squared times h plus u naught, where u naught is equal to u sub g of r naught. It's just equal to this term here. In this case, it would be equal to negative gmm over r naught. So now, let r naught be the radius of the Earth, and m be the mass of the Earth, right? And assume h is small relative to the radius of the Earth. With these parameters in place, we can calculate to good approximate values the gravitational potential energy near the surface of the Earth. That gives us that u sub g as a function of h now, because r naught is just a fixed thing, it's just the radius of the Earth. This is equal to mgh plus u naught. And why is that? Well, mg is equal to gm, that should be using a lowercase m, g mass of the Earth times m over the radius of the Earth squared. That just is how mg, or that is how g is defined. And u naught, in this case, is just the standard, or the Newtonian gravitational potential of r naught. But remember that we can just drop constants, right? That's just a thing that we can do. And so we can just get rid of this, and that's how we get that the potential energy due to gravity is just mgh. The reason why we're allowed to do that is because if you zoom in close enough, the first order non-trivial, or the first non-trivial term in the Taylor series expansion is a linear term. And that gives us a constant gravitational force, because once you take a derivative with respect to your variable, you get a constant. In this case, take a derivative with respect to h, you get a constant mg. So Christine asks, why do we use Taylor series instead of just taking the derivative at the point r naught, since it's linear? That doesn't, so the point is that it's not linear. It's not actually linear. It goes as 1 over r, but assuming that your height is small compared to the radius of the Earth, which we typically do, 100 meters or so, then it's fair and it's reasonable to approximate the function as linear. And by using the Taylor series of expansion, this gives us the built-in this gives us the best approximation to our potential energy function as a linear function. This is the best approximation at that point R naught that has a linear structure. The whole idea is that what we did is we took something that's otherwise complicated, and thus the gravitational force would be complicated, and we said, okay, so what would be the first non-zero, or what would be the most significant part of the force that how do I want to phrase this? What would be the dominant factor near the surface of the Earth in the force? And it turns out the dominant factor is just this mg term. And there are other lower order terms that are less dominant, and those would come from higher derivatives. Things like you would have basically an h squared term, you'd have an h cubed term, and so on, but those get smaller and smaller because the terms that you're interested in or the forces would be h over r naught. And so we don't keep those because those are very, very small. But at the end of the day, the gravitational function that we use for standard Earth-based things is the same as Newton's law, universal law of gravitation. It's just a linear approximation of that law. Now, there was a good question in the Discord that Max asked, and I do want to highlight that. The question is why is it that here the gravitational potential energy is positive, whereas when we're talking about gravitational potential energy for the for things orbiting other things, it's negative? And that just has to do with the choice of constant that we make. Right, so when we were deriving the potential energy function, we made a choice and said, look, we want to choose this constant to be 0 so that the gravitational potential energy is 0 when r is infinitely large, when you're infinitely far away. However, we make a different choice of this constant when we work with, say, the surface of the Earth. We instead choose, we want the gravitational potential energy to be 0 at the surface of the Earth. And so all that does is it just shifts this graph up and down, choosing different constants. And so by shifting the graph upwards, like it's still true that regardless of whether it's positive or negative, as you go further away, your potential energy increases. We've just chosen where we want to put the 0 point. So in fact, if you actually included this constant here based off of the constant that we used the previous choice, you'd find that the gravitational potential energy at the surface of the Earth is indeed negative because this u naught is less than 0. And in fact, it's less than it would be a fairly large negative number. And that's just a fact. So indeed, it is negative if you choose the same choice of constant of integration, but we don't have to make that choice. And so we use the more straightforward one for the surface of the Earth. Hopefully that answers that question. Right. So just like when we were first starting to talk about potential energies, one of the things that we did then was we said, okay, we have this potential energy function. What can we do with it? Well, one thing you can do is you can plot it. Because once you have kinetic energy and potential energy, you can use energy diagrams to analyze the behavior of a system. And so we now have a potential energy function here, up here. And so now, and we know what the kinetic energy is, it's just 1/2 mv squared. So we should be able to do the same thing to be able to better analyze systems, especially systems that are bound, meaning that they have a minimum and maximum position. Say in this case, it would be a minimum and maximum distance from the object that it's orbiting. And so if we can use, it is wise to use energy diagrams to do that analysis. So we're going to talk about how that works in the case of gravity. So one thing that we have to be aware of when we're thinking of energy diagrams is that in the past, the energy diagrams only cared, or rather, they only, what's the word I'm looking for? They only modeled one-dimensional motion. Meaning, we ignored any velocity in the horizontal, like let's say that we were talking about the energy diagram for gravitational potential energy near the surface of the Earth. Well, in that case, we only modeled the vertical direction, and we didn't care about potential or kinetic energy horizontally, for example. However, the total energy of a system, when you're talking about bodies orbiting other bodies, definitely matters. It's not just enough to talk about the energy in a single direction, because depending on what direction it's moving in, it will have a different shape of orbit, and we need to be able to incorporate that into our analysis. So just as a concrete example, let me show you what might happen if we just treated everything as one-dimensional, just use r as our one-dimensional variable, and then just proceeded from there. So let's try using just u sub g of r for an orbit that is elliptical. So the potential energy graph doesn't change. It's still just negative gmm over r squared. Sorry, over r. Stop it. So it still looks like, oop, terrible. Still looks like that. And so what would happen for an object that has this potential energy that is moving towards perihelion? If an object is moving towards perihelion, that means that its radius is getting smaller, right? Sorry, not the radius. The distance that the object is from the gravitating body is getting smaller. So that would mean that it has a velocity this way. And let's say perihelion is, say, somewhere over here. It's at some other distance, r sub perihelion. Well, according to our model then, that means that it'll just move to the left, and there will be a force pulling it in towards the left. We know that the forces that are applied is always towards lower potential energy, and so if we look at this plot, you'd see, oh, well, the lower potential energy is to the left. So the object would just accelerate more and more to the left. And eventually, it would just crash into the thing. But we know that that's not what happens. This model predicts that the object just falls into the sun. And that's clearly not what happens for all orbiting bodies. Indeed, for for bodies that are actually orbiting, orbits involve turning around and going back to aphelion. So how do we incorporate that into our model? We want to be able to include some sort of barrier or some sort of feature of our model, of our energy diagram, that tells us that the object turns around and returns to a further distance. Just like how if we were modeling, say, the spring, we would find that as an object moves to the left, it'll approach a minimum distance, and then it'll turn around and go back to the right. And then it'll do the same and rinse and repeat. We want to incorporate that same sort of structure to our energy diagram here. But if all we have is just this gravitational potential energy function, that just doesn't happen. Now, one thing to keep in mind is that this is all there is if the object only has radial velocity. If all of the motion takes place in the radial direction, i.e. the object is not moving relative to the sun, it's just moving backwards or forwards, then it is indeed true that the object will just fall into the sun. Where things start to break down is when things start to have non-zero angular momentum. What I mean by that is once things start to have velocity that is not in the radial direction, i.e. towards the sun, but velocity that's, say, perpendicular to that direction, like the Earth's velocity, then there's this idea that you can approach the sun, but still miss it and swing back around. That's what we're trying to model here. So just as when we talked about, say, gravitational potential energy on the surface of the Earth using an energy diagram, let me write out some words. Let's say for u equals mgy. We did not include, say, 1/2 mvx squared, the horizontal part to the kinetic energy. We cannot include, say, 1/2 mv tangential squared in our kinetic energy here. And that's because that tangential part of the velocity is not affected by the, it's not directly affected anyway, by the force applied in the radial direction, right? This force that I've drawn here, this is a force in the radial direction because we're plotting r versus energy. And so the gradient of this function is with respect, or the derivative of this function, the slope here, is with respect to r, so that points in the r hat direction, i.e. in the radial direction. So we need to somehow separate out our tangential piece of the kinetic energy. And we can't just say it's zero, because it's certainly not. It does contribute. If you have larger tangential kinetic energy than you do radial kinetic energy, then your orbit will be faster, but you won't necessarily crash into the sun. So we basically want to figure out some way to split them in a way that's consistent and will let us handle these energy diagrams. So the fix here is to just do exactly as I said, just split the total kinetic energy into two parts. You have kinetic energy that's in the radial direction, or kinetic energy coming from the velocity in the radial direction, and then all of the other kinetic energy. This is kinetic energy in the tangential direction. And so just so I'm clear what I mean, let's say that you have, say, the sun, and I have to draw two circles. One is or I have to draw an ellipse and a circle. So say we're talking about the object as it is here. So at that moment in time, the object has a velocity that points, say, that way, right, as it's orbiting around. But when we say tangential, we do not mean tangential to its orbit. We mean tangential to the circle or tangential to the radial, or perpendicular to the radial direction. So really, when we say tangential velocity, we mean there's a part of the velocity that's this way. That would be v tangential. And then there's a part of the velocity that's, say, let's see if I can draw this right. Let's say this way. That would be v radial. And so what we can do is we can just write that the total kinetic energy is just equal to the sum of the kinetic energies from each of those separate velocities. So here we have that the tangential kinetic energy is 1/2 times the mass of the orbiting body times v tangential squared. And now I'm going to use a trick here that lets us get rid of this tangential notion, or this, like, lets us get rid of the tangential velocity and trade it for a distance. So I want you guys to recall that for any object that's moving, the angular momentum, the magnitude of the angular momentum, which usually we just call L, without the bars as a vector symbol, is the mass times the velocity, it's just the momentum, times the radius, the distance from the pivot point to the object, times the sine of the angle between the radial vector and the velocity vector. Now, typically what we would do is we would group r and sine theta together, and we would just say, okay, look, that's called the moment arm. But we can do a different grouping here. We can group this as m times r times v sine theta. And this v sine theta, when you define, or when you're meaningfully talking about the correct theta, this v sine theta is the tangential velocity. And so what we have is that we have that L is mr times v tangential. And so because the angular momentum is conserved for a given orbit, like, for example, this orbit up here, we can just treat L as a constant and rewrite this tangential velocity in terms of L and other quantities. So that gives us that the tangential kinetic energy is equal to L over 2mr squared. And that's useful because now we can write the total energy as just things that depend on the distance and the speed in the radial direction. So we would write E total equals KE radial plus KE tangential plus the gravitational potential energy. And so substituting everything in, this is 1/2 times m times v rad squared. That's just the tangent, or the radial velocity, which is exactly what we need this to be in terms of, plus L squared over 2, L, not L squared, L over 2 mr squared minus gm m over r. And so now written like this, we can treat this as a one-dimensional system. Now all of the motion of the system is captured either by the radial kinetic energy. This is just in terms of the time derivative of the distance between the two objects, which is exactly what we expect to show up in our graph, and the other kinetic energy, which is now written again in terms of something that only depends on distance. So what we do, by capturing all of that angular motion in a radially dependent term, we can instead define a new function called the effective potential. And we call it U sub EFF. And that's just a function of R. I may have dropped an L. Let me double check. Yeah, this should be L squared. There we go. Yeah, that should check out. Thanks for the check, though. Yeah, that seems more right anyway. Yeah, I just dropped it. I just dropped an L. Right. Where was I? Right. So we can define this new effective potential as L squared over 2mr, 2mr squared minus G capital M lowercase m over R. And so with this definition of the effective potential, now we can plot this, and we can see what I mean, well, let me stop talking and actually plot it so you can see what it looks like. So here we have energy going up and down. We have the distance between the two bodies going left and right. And so this plot looks like this, where this is the effective potential as a function of R. And so what we find is, if, say, our system has some total energy which is conserved, say E tot, now we can look and see what happens at various turnaround points like we've noted before. This point would be the minimum value, the minimum distance that the object can get from the other object. We would call that the perihelion. This distance here would be the maximum distance that the object can get. This would be the aphelion. And so, and maybe we call this middle point here, maybe we call it R naught or something, just for the sake of plotting. And so the turnaround points make sense now. The reason why there are turnaround points with this effective potential is that because the angular momentum is conserved, if the distance between the object and the gravitating body decreases, the speed has to increase. That's just conservation of angular momentum. And so, but we know that think my headset just shut off. If the speed increases, this is tangential speed now, because that's where the distance and the angular momentum are related. If the tangential speed increases, that means that the tangential kinetic energy decreases. But the system has a has a fixed amount of total energy, and so you can't just increase your tangential kinetic energy forever. It's just not allowed, because you have a finite amount of energy. And so, and in particular, the maximum amount that the speed can increase to is the value that you would get when you find this perihelion distance. You'd plug it in, you'd find the gravitational potential energy decreases it somewhat, but then the tangential kinetic energy increases it again. And there's just a fixed value there. So what this does, by introducing this extra term, L squared over 2mr squared, this introduces it's like a centrifugal, it's often called a centrifugal barrier. Basically, if an object is going around in a circle, if you kick it in closer, it's not going to, it takes, how do I want to phrase this? If something has enough energy, in particular energy in the form of angular motion, there is something blocking the object from actually hitting the object. And that's because it has angular motion, and that contributes to angular momentum, which means that the object will instead just swing around whatever object you're talking about and not actually hit it. That's what this is. This is a centrifugal barrier. And it's really there. If you want to model gravitational or any sort of radial motion, or sorry, circular motion or elliptical motion, in terms of one variable, a one-dimensional problem, you have to include this centrifugal barrier. That's not to say that this is a potential energy, and that's because there is no potential energy that has this, that will have this, sorry, there is no actual force that has this shape. You might say, oh, we'll take the derivative of this and then you'll get some force. That's kind of true. You would get something like a centrifugal force, but that's not a real force. So this is just a way of modeling the gravitational dynamics that we're talking about. Just as a word of caution, when we were talking about energy diagrams in the past, and we would have this minimum and maximum values, at those points, we said, oh, well, the total energy is just the potential energy. So that means that the kinetic energy is 0. That's not true here. Here, when the total energy is equal to, say, U effective of, say, R peri or something, when the total energy is this value, that only means that the radial component, or the radial contributor to the kinetic energy, is 0. And that kind of makes sense, right? At perihelion, the object is no longer falling towards or away from the object. At perihelion, the object is going perfectly tangential to a circle that would enclose it. Similarly, at aphelion. And so the radial velocity is 0. That's certainly true. So just like we did before, we can analyze what it means for a system to be bound, or for a system to be unbound. And so what we can actually do using this new effective potential is we can actually do orbit categorization. What I mean by that is we can start talking about what types of orbits or trajectories there are. And it turns out that there's 3 types. Oh. So the first type is, I guess there's 4 types, but one of them is a special case. So the first type is a circular orbit. It's the most basic. So when would that happen? A circular orbit means that the distance between the 2 objects is fixed. It means that the radius doesn't change. So the only place that could happen is down here, where there is no room for the object to go further away and closer. If the total energy is equal to the minimum value of the effective potential energy, then R min, or our the perihelion distance, is equal to the aphelion distance. And the radial component to the kinetic energy is just 0, and that makes sense. At that point, the distance never changes, and that's precisely what a circle is. A circle is the set of all points for which the distance is the same from the center. Further, if the radial kinetic energy is 0, what does that mean? It means that any kinetic energy it might have has to be tangential. And so that means that the object is traveling in a perfect circle, because traveling in a circle means that you have tangential velocity. If it wasn't a circle, you would end up, if the velocity was not all tangential, you would end up with shapes like an ellipse. Oh. So that's one type of orbit that you can get. Elliptical orbits, well, there's nothing really to talk about there. This just occurs when the total energy is less than 0. Then you have, I should say, when the total energy is less than 0, but greater than the minimum. Otherwise, you have a circular orbit like above. If that's true, then the perihelion distance, I can't write today, is less than the aphelion distance. And that's just by looking. Like if your energy is, say, this line here, then you're going to have some perihelion distance, which is found by matching the effective potential to the total energy. And in aphelion distance, you'll have 2 separate points, and one will be larger than the other. And then you can just talk about things like, well, what's the how much kinetic energy does it have in the form of radial kinetic energy at various points? And that's a calculation that you can do, and it's relatively straightforward. It's just a generalization of a circular orbit. The next more interesting thing, though, is a parabolic trajectory. And notice that I'm changing language from orbit to trajectory, because orbit implies that it keeps going forever in that, like in some sort of repeating motion. But that doesn't happen for parabolic trajectories. For parabolic trajectories, we have that the total energy is precisely equal to 0. When that happens, whatever object is under the influence of gravity is said to be in a parabolic trajectory. And what that means is that the object just barely escapes. It just barely escapes orbit. So it'll go off towards infinity, but it'll have 0 velocity when it does. The reason, by the way, why we call it a parabolic trajectory is that the shape is a parabola. I think my headset's dying. I'm going to plug it in really quick. We're about to get there. The last type of orbit that we can categorize is the hyperbolic orbit, or hyperbolic trajectory, rather. And that is precisely when the total energy is greater than 0. This is similar to a parabolic trajectory, except in this case, we have that there is kinetic energy. Sorry, radial kinetic energy. It's not equal to 0, even when infinitely far away. Yeah, I'll draw a picture in a minute for all of these. This shape, just like how in the parabolic trajectory, the shape is a parabola, for a hyperbolic trajectory, the shape is a hyperbola. And you guys have heard of those and seen those in class. So let me draw what a parabolic trajectory would look like. And it's going to be kind of hard to see how it's different from a hyperbolic trajectory, but the idea is that the object comes in, but it has so much energy that it just comes in and then it just swings out. So this would be an example of something well, we don't really see parabolic trajectories in real life because you have to perfectly fine-tune the the shape of or the energy. But we do see hyperbolic trajectories a lot, so this is like a parabola. Notice if I turned it on its side, it would be a parabola, right? A hyperbola, it's hard to draw, to show, but let me do my best. So I'm drawing some guidelines for myself here. So a hyperbolic trajectory, or a hyperbola, unlike a parabola, a hyperbola, as distance goes to infinity, approaches the lines y equals x and y equals minus x. So in this case, this is a hyperbola, and they look very similar. It's just in the hyperbolic trajectory, it goes out faster. And you'll notice here, by the way, that even as the distance away goes to infinity, it still is always going in the radial direction. It's always still has some radial velocity. If a rocket went up and to the side, but doesn't make its orbit, does that count as a parabolic trajectory? Right, so Henry, so this is where the, I want to say yes, but I'm not going to say for certain. That's why I didn't mark this as an angle. I believe yes, but I think that you could, like, a hyperbola in general doesn't have to have a 90-degree angle between them, but that's something that you can tune. So let me answer Henry's question. So if a rocket went up and to the side but doesn't make its orbit, does that count as a parabolic trajectory? Right. So that is a parabolic trajectory, but only if you model it using mg, the F equals mg. If you model it using Newton's universal law of gravitation, no, it's not parabolic. In fact, it's just a segment of an ellipse. Because what happens in that image is that you have your rocket go up and then comes down. But that's because if you were to complete the orbit, it would look like that. It would actually be in orbit, about the center of the Earth. But because the Earth is, solid, we only see this part. But it can be approximated as a parabolic trajectory for a different reason. If a spaceship were to slingshot around a planet, e.g. the Voyager, would that be an example of parabolic or hyperbolic trajectory? It'd be an example of a hyperbolic trajectory, unless it's perfectly fine-tuned, in which case, there'd be no reason to do that. All right, so I do have a little bit more to talk about, and that's something that's kind of neat. So I'm going to finish so falling objects actually fall under elliptical and not parabolic paths? Yeah, but we don't model them using Newton's law of gravitation anyway. We model them using mg. And, when you're sufficiently close to the Earth, parabolic and elliptic trajectories are the same. Like they're one approximates the other. Right, so I mentioned this idea of escaping to infinity, right? It barely escapes orbit. So let's talk about escape velocity. So it turns out that the way we define escape velocity is it's not actually that surprising. We define escape velocity to be the velocity needed, the radial velocity needed, by the way, needed so that the total energy is 0, starting at some fixed distance, say capital R. And in fact, so often we only talk about the radial component of the velocity being the escape velocity, but really, if you're already in orbit, you can change your regular velocity, you can change your velocity in general so that the total energy is 0, and you can still escape. You'll just escape starting from orbit instead of escape starting from just stationary. Yes, Christine, that is true. So let's just write what the total energy has to be. The total energy has to be 0. So this is 1/2 mv rad squared plus u effective of r. This is starting at a distance r. So the total energy has to be 0 at that position r. And so we can rewrite this as just 1/2 m times v squared, where v is the full velocity, plus the gravitational potential energy at a distance r. And that gravitational potential energy, u of r, is negative g capital M times little m over capital R. And so we can solve for the escape velocity. The escape velocity, starting at a distance r, is square root of 2gm over r. So it's just a matter of setting your total energy to be 0. Now, What's funny about this is that in order to escape an object's gravitational influence, it doesn't care at all about how heavy the object is that's doing the escaping. It only cares about how fast the object is moving. So this brings up a funny question then, where we can ask, what about light? So light has no mass. Hopefully you've learned that before. If not, this is news to you, but maybe it's not surprising. Light indeed has no mass, but it does have a speed. So what does that mean? Does that mean that it's possible for light to be gravitationally pulled into an object if the speed of light is less than the escape velocity? It turns out the answer is yes. It turns out that light is affected by gravity, although Newton didn't know it. That was an Einstein thing. And we can just figure out the radius that an object has to be. We can just figure out the radius of an object of some mass, capital M, from which light cannot escape. The idea is that there could be an object that has a mass M and radius R that light wouldn't be able to get off of the surface from. If you shined a flashlight up, it wouldn't go up. It would just come back down. So given a mass capital M and the radius of our body, if we want to figure out how much mass it has to have so that light can escape from a given radius, we would just plug in the velocity of light, which we call c. So if the escape velocity is to be the velocity of light, that would mean that we have the following relationship. C is equal to 2gm over capital R. And so we can just solve for how small an object has to be so that its escape velocity is the speed of light. And that is equal to R sub s, which has a name, it's just 2gm over c squared. So the idea is that if you have, if you have something of a particular mass, and you want to ask how much speed does something need to have in order to escape at a fixed radius, well, let's just say that the radius is the surface of that mass. If you want it to be the case that light cannot escape, then you just need that mass to be all within some fixed radius, whatever that radius might be. So this radius, called the Schwarzschild radius, German names have a lot of consonants in a row, R, Z, S, C, H, named after, I forget his name, a guy named Schwarzschild in 1915. That is the distance that an object has to be given a mass so that light cannot escape. So in fact, this is actually the size of a black hole. So for Earth, you might ask, how close does light have to be to the center of the Earth in order to not be able to escape the Earth's gravity? It turns out that the Schwarzschild radius of the Earth is say this is due to the mass of the Earth, is something like 8.8 millimeters. But so it's not like if you drilled down, 6,000 whatever 400 kilometers, and then you shined a light, it wouldn't escape. The point is that the object, all of the object's mass would have to be within 8.8 millimeters, would have to be within a sphere of 8.8 millimeter radius. So if you contracted all of the mass of the Earth down to a p, that's approximately 18 millimeters across, then light would not be able to escape the surface of that p-sized Earth. And yes, this is indeed the radius of the event horizon. This is how the event horizon is defined. Well, not quite, but colloquially speaking, the event horizon is defined as the distance that you have to be from a certain amount of mass such that light can no longer escape. And this is what happens when you create a black hole. A black hole is a very, very dense object with a lot of mass in a very small region. And so outside, this is the speed of light. If you shine a light closer, if you shine a light, say upwards, away from the object, but that light started out closer than this Schwarzschild radius, given whatever the mass is, then that light would never make it out. The idea is maybe you have a whole lot of mass at a very, very small point, and maybe this is the Schwarzschild radius for that amount of mass. This has mass m, maybe this distance is r. If you were standing here and you shone a flashlight, that light would just come back around. It would never actually escape. And so this is indeed what a black hole is. So it turns out that Newtonian gravitation actually can get you black holes, but they didn't know that light was affected by gravity to begin with, so that's why they didn't think of it then. By the way, funny story, maybe less funny story. The Schwarzschild radius by the guy named Schwarzschild was determined in the middle of World War I, in 1915, I think. So the German fellow, let me Google his name just so I stop referring to him as his last name. Carl Schwarzschild. So Carl, when he was discovering, or when he was calculating and doing all this, like doing this brand new research at the time, he was actually in the trenches on the Eastern Front. He was German. He was fighting for the Germans in World War I, fighting the Russians. He was actually in Russia, in trenches, when he discovered this, and he sent a letter to Einstein via snail mail during that war. It turns out he actually didn't survive. He did not survive the war, but his work got to Einstein because he sent a letter. He actually died less than a year later, and it was you know, it's I guess it's a good thing that he sent his work to Einstein. Otherwise, we probably would have been behind at least probably a decade. But yeah, it's kind of a sad story. But he loved this stuff so much, he was doing it while shells were being dropped on him in the trenches. Anyway, so that was just a little bit of some modern physics.